नमस्कार, मैं आनंद कुमार खत्री, एसोसिएट प्रोफेसर ऑफ जूलॉजी, गवर्नमेंट डूंगर कॉलेज बीकानेर। आज के हमारे लेक्चर का विषय है अर्थ एटमॉस्फेयर। पार्ट फर्स्ट। एटमॉस्फेयर, the gas and aerosol envelope that extend from the ocean, land and ice covered surface of a planet outward into space. The density of the atmosphere decreases outward because the gravitational attraction of the planet, which pulls the gases and aerosols inward, is greatest close to the surface. Atmosphere of some planetary bodies such as Mercury are almost non-existent, as the primordial atmosphere has escaped the relatively high, relatively low gravitational attraction of the planet and has in this environment must have been anaerobic. In addition, they must have been able to resist the biological destructive ultraviolet radiation in sunlight, which was not absorbed by a layer of ozone as it is now. Once organism developed the capability for photosynthesis, oxygen was produced in the large quantities. The buildup of oxygen in the atmosphere also permitted the development of the ozone layer, as O2 molecules were dissociated into monatomic oxygen consisting of single oxygen O and recombined with the other O2 molecules to form triatomic ozone molecule O3. The capability for photosynthesis arose in primitive forms of plants between 2 and 3 billion years ago. Previous to the evolution of photosynthetic organism, oxygen was produced in limited quantities as a byproduct of the decomposition of water vapor by ultraviolet radiation. The current molecular composition of Earth's atmosphere is diatomic nitrogen 78.08%, diatomic oxygen 20.95, argon 0.93, water H2O. 0 to 4%, carbon dioxide 0.04%, and inert gases neon, helium, krypton, and other constituents such as nitrogen oxide compounds, sulfur, and compounds of ozone are found in lesser amounts. Surface budget, energy budget. Earth's atmosphere is bounded at the bottom by water and land. That is, by the surface of the earth. Heating of this surface is accomplished by three physical processes: radiation, conduction, convection, and temperature. At the influence of the atmosphere and surface is a result of this heating. This is the earth's environmental sphere, showing atmosphere, hydrosphere, lithosphere, and biosphere. The relative contribution of each process depends on the wind, temperature, moisture, structures of the atmosphere immediately above the surface, the intensity of the solar insolations, and the physical characteristics of the surface. The temperature occurring at this interface is of critical importance in determining how suitable a location is for different forms of life. Radiation. The temperature of the atmosphere and surface is influenced by the electromagnetic radiation, and this radiation is traditionally divided into two types: insolations from the sun and emittance from the surface and the atmosphere. Insolation is frequently referred to as short wave radiation. It falls primarily within the ultraviolet and visible portions of the electromagnetic spectrum and consists predominantly of wavelength 0.39 to 0.76 micrometer. Radiation emission emitted from Earth is called long wave radiation. It falls within the infrared portion of the spectrum and has a typical wavelength of 4 to 30 micrometers. Wavelength of radiation emitted by a body depends on the temperature of the body as specified by the Planck's radiation law. The sun, with its surface temperature of around 6000 Kelvin, emits at a much shorter wavelength than does Earth, which has lower surface and atmospheric temperature around 250 to 3300 Kelvin. A fraction of the incoming shortwave radiation is absorbed by the atmospheric gases, including water vapor, and warms the air directly. But in the absence of clouds, most of the energy reaches to the surface. The scattering of a fraction of the shortwave radiation, particularly of the shortest wavelength, by air molecules in a process called Rayleigh scattering, produced Earth's blue skies. When tall, thick clouds are present, a large percentage, or up to about 80% of the insolation is reflected back into the space. The fraction of the reflected short wave radiation is called the cloud albedo. Of the solar radiation reaching Earth's surface, some is reflected back into the atmosphere. Value of the surface albedo range as high as 0.95 for fresh snow to 0.10 for dark organic solids. On land, this reflection occurs entirely at the surface in water. However, albedo depends on the angle of the sun's rays and the depth of the water column. If the sun's rays strike the water surface at an oblique angle, albedo may be higher than 0.85. If then these rays are more direct, only a small portion, perhaps as low as 0.202, is reflected, while the rest of the insolation is scattered within the water column and absorbed. Shortwave radiation penetrates a volume of water to significant depths, up to several hundred meters, before the insolation is completely attenuated. The heating by solar radiation in water is distributed through a depth, which results in a smaller temperature changes at the surface of the water than would occur with the same insolation over an equal area of the land. Earth exists and sunlight. The amount of the solar radiations reaching the surface depends on the latitude, time of year, time of day, and orientation of the land surface with respect to the sun. And in the northern hemisphere, north of 23 degree 30 minutes. For example, solar ray insolation of at local noon is less on slopes facing the north than on land orient towards the south. Solar radiation is made up of direct and diffuse radiation. Direct short wave radiation reaches the surface without being absorbed or scattered from its one line of propagation by the inner intervening atmosphere. The image of the sun's disk as a sharp as distinct object represents that portion of the solar radiation that reaches the viewer directly. Diffuse radiation, in contrast, reaches the surface after first being scattered from its line of propagation. On an overcast day, for example, the sun's disk is not visible and all of the short wave radiation is diffuse. Long wave radiation is emitted by the atmosphere and propagates both upward and downward. According to the Stefan-Boltzmann law, the total amount of the long wave energy emitted is proportional to the fourth power of the temperature of the emitted material. Example, the ground surface or the atmospheric layer. The magnitude of this radiation reaching the surface depends on the temperature at the height of emission and the amount of absorption that take place between the height of the emission and the surface. A larger fraction of the long wave radiation is absorbed when the intervening atmosphere holds large amounts of the water vapor and carbon dioxide. Clouds with liquid water concentration near 2.5 grams per cubic meter absorb almost 100% of the long wave radiation with a depth of 12 meters into the cloud. Clouds with lower liquid water concentration requires greater depth before complete absorption is attained. For example, a cloud with a water content of 0.05 gram per cubic meter requires about 600 meter, about 2 feet for complete absorption. Clouds that are at least thick, this thick emit long wave radiation from their bases downwards to the earth's surface. The amount of long wave radiation emitted corresponds to the temperature of the lowest level of the cloud. Conduction. The magnitude of the heat flux by conduction below a surface depends on the thermal conductivity and the vertical gradient of the temperature in the material beneath the surface. Soil such as dry peat, which has very low thermal conductivity, permit little heat flux. In contrast, concrete has a thermal conductivity about 75 times as large and allows substantial heat flux. In water, the thermal conductivity is relatively unimportant since, in contrast to a land surface, insolation extends to substantial depth in water. In addition, water can be mixed vertically. Convection. Vertically, vertical mixing convection occurs in the atmosphere as well as in bodies of water. This process of mixing is also referred to as turbulence. It is a mechanism of heat flux that occurs in the atmosphere in two forms. When the surface is substantially warmer than the overlying air, mixing will spontaneously occur in order to redistribute the heat, and this process referred to as a free convection occurs when the environmental lapse of temperature decreases at a rate greater than 1 degree centigrade per 100 meter. This rate is called the adiabatic lapse rate, the rate of temperature change occurring within a rising of the or descending air portion. In the ocean, the temperature increases with the depth that results in free convection is dependent on the temperature, salinity, and depth of the water. For example, if the surface has a temperature of 20 degree and a salinity of 34.85 parts per thousand, and increase in temperature with the depth of greater than about 0.19 degree per centigrade per kilometer just below the upper layer of the ocean, will result in free convection. In the atmosphere, the temperature profile with height determines whether free convection occurs or not. In the ocean, free convection depends on the temperature and salinity profile. With depth, colder and more saline conditions in the surface parcel of water, for example, make it more likely for that parcel to sink spontaneously and thus become part of the process of free convection. This is the picture showing the rising air in unstable atmosphere. Mixing can also occur because of the shear stress of the wind on the surface. Shear stress is the pulling force of a fluid moving in more in one direction as it passes close to a fluid or object moving in another. As a result of surface friction, the average wind velocity at Earth's surface must be zero unless that surface is itself moving, such as in river or ocean currents. Winds above the surface decelerate when the vertical wind shear becomes large enough to result in vertical mixing, the process by which heat and other atmospheric properties are mixed as a result of wind shear is called forced convection. Free and forced convection are also called connective and mechanical turbulence, respectively. This convection occurs as either sensible turbulent heat flux or latent turbulent heat flux. When this mixing does not occur, wind speeds are weak and change little with the time. Plumes from power plant stacks within this layer, for example, spread very little and the vertical remain in close proximity to the stacks. Thanks.